Okay, so you remember in the previous class, we started discussing two-body problem, right? Central force problems. And so now let's continue that. So yeah, we got what? We got the Lagrangian. We wrote down Lagrange equations for R, for theta. Theta is cyclic, so of course corresponding generalized momentum, which is the angular momentum, is conserved, right? So we got that. And we also get the second order differential equation, which can be used to solve any problems of this type. Right, and that's what we used in undergraduate level course. I wrote it down, but now let me just write that second order differential equation as one of the options which can be used to solve problems, two-body problem. And so that equation was mr double dot, right, minus L squared over mr to the power of 3, right, and equals to f as a function of r. So that was our first option, right? First option which can be used. And again, as I said, we used this equation in undergraduate level course. And also in the previous class, we wrote down the integral of motion, basically conservation of mechanical energy, right? So the second option, okay, maybe probably I should write this. So in the second option, it's the mr dot squared over 2, then plus L squared over 2mr squared, and plus potential energy, and equals to E. So that's the second option, which can be used. Of course, it's a first order differential equation, which can be used to solve problems like this. And of course, it doesn't matter which approach you take, you can solve it for two types of solutions, right? So let's just say it. So you can solve it, or them, for, probably let me write it like, yeah, let me write it this way. So you can solve it for r as a function of time and theta as a function of time. In this case, of course, you can easily get velocity of a particle, right? You can get the history of the system, right? So you can get plenty of information which might be useful. Or sometimes people are not interested in that. Sometimes people are interested in trajectories, right? And of course, you can solve it for r as a function of theta trajectory. So there are two types of solutions. Right. And again, but most of the time, still people are interested in this. And again, since we are moving in today, we will start discussing scattering. Of course, we will need this solution. Right. So let's play with this integral in order to get, I mean, this first integral of motion, in order to get integrals which can be used to solve for this solution, and then integral which can be used to solve for that. And then, of course, after that, we will move to scattering. So, all right, probably I should, of course, say that we're going to use this second approach, right? And so first, let's get integrals which can be used to solve for time dependencies. Of course, we need to solve it for r dot. R dot will be equals to square root of 2 over m, and then E minus V and minus L squared over 2 mr to the power of 2, right? So that's dr over dt, right? And so now we just basically need to separate variables, right? So r here, r there, so it must be on one side, and t must be on the other side, right? So of course we can get immediately the integral. So from here we can get the t equals integral from some r naught to r, right? If you want to deal with a definite integral or indefinite, it's up to you, right? And you will have dr divided by this mass 2 over m. You know what, probably, oh no, I'll keep it like this. Yeah, I'll keep it like this. 2 over m e minus, e minus v and minus L squared over 2 mr to the power of 2, and we can close square root sign. So, of course, you can take this integral, and as a result, you will get what? You will get, my line are not straight. You will get t as a function of r, but of course, then you'll have to invert it in order to get r as a function of t. So basically, that's the, of course, approach to get dependence of r on t. How can we get theta? From the conservation of angular momentum, which we got from the theta equation, right? You remember Lagrange equation for theta. So we got L equals mr squared theta dot. Of course, from here, we can get what we need, right? So you will get d theta over dt. It will be L over mr squared, right? R dependence goes over there and integrate. So we can actually, let me move dt to that side immediately to save space, right? So dt, right? And then integrate it. And of course, r goes into there. And as a result, you will get theta as a function of t if you integrate it properly, right? So you'll get integral of L dt and divided by mr. Okay, probably I should emphasize on type dependence. R as a function of t. No, that's okay. It's good. No, I think I need to rewrite it. It's better. R to the power of 2 and as a function of r. Function of t. Okay, so from here, of course, you will get theta as a function of time. Okay, I will just frame it with green, since it's not the most important. But as I said, we will be interested in this, or we are interested in that, right? So it means that we need to rewrite this integral, right? I will probably do it from this point, right? So I will just write in a differential form, right? Okay, let me write, but we want r as a function of theta, right? So as a result, our integral must be rewritten, right? We need to get rid of time and insert theta. Okay, so let me write this in a differential form, as I told you, right? So dt equals to dr divided by the square root 2 over m e minus v minus L squared over 2m r squared, right? And so how can we get rid of time and insert theta? We can use this, the first integral of motion, right? So we can get dt from here, replace this dt, and that's it, right? So let me open my explanation box to show that I'm using this. L equals mr squared theta dot. Of course, as a result, from here, dt will be equal. Dt downstairs, go there. So it will be mr squared over L d theta. I think it's true, correct. Let me check. Yeah. So we can write instead of that dt. So it will be mr squared over L d theta. So let's just move this stuff to that side, and we can get integral for theta, right? It will be as a function of r, right? But of course, if you take integral, then you can invert it, all right? And to get dependence, r as a function of theta. Okay, so let me write. Okay, I will write immediately. Theta will be integral, right? Indefinite integral, or maybe definite. Okay, let me write definite, right? Integral r naught to r. This goes up here, L dr divided by mr squared, and that's square root. Oh yeah, first of all, yeah, 2 over m e minus v minus l squared over 2 mr squared. Okay, so now we have to make some cosmetic changes. I just want to take L inside of this square root sign and M also inside, right? And I will probably just write underneath, right? And after this, yeah, I will move to that side. So finally, theta equals integral from some initial to some arbitrary final position. And dr will be by itself. Then r squared, we cannot do anything about that. All right. And then square root of m will go inside, it will be m squared, so as a result it will be in the denominator, 2me over l squared. This l will go downstairs. Then the same with v, minus 2mv over l squared, right? And here 2 gets cancelled, m disappears, so it will be just minus 1 over r squared. And I can close my square root sign. Looks correct. Of course, v potential, it's a function of r, right? It's a function of r, right? Because our forces are conservative, so there shouldn't be any finicky dependence of v, only on r. Okay, so then, so yeah, you can apply it to find trajectories of any particles, right? But of course, and nothing wrong with this integral, but every time when you have to take this integral, your first step will be, you will try to get rid of this r squared in the denominator. It ruins the whole picture. And every time, in order to get rid of this r squared, you will make the same, exactly the same step substitution. R equals 1 over u, or something like this, in order to get rid of that r squared, right? So as a result, if you're going to do it all the time, it makes sense to rewrite this integral in terms of that new variable u, right? Okay, so let's make a substitution. And we're going to write, so u equals 1 over r. And of course, du equals to minus dr over r squared. Basically, this construction, this part, it is equal to minus du. So this substitution allows us to get rid of that r squared, which spoils the whole nice, otherwise nice picture. Okay, probably I can squeeze it still downstairs. I mean here, below. Okay, so as a result, I can write integral. So theta will be equal. Or to do minus in front. Almost forgot. Minus integral from some u naught to some value u. Right? Then du and square root of, yeah, so pretty much the same except for minus u squared, the last term. So it will be 2m, it's difficult to write here, l squared, minus 2mv over l squared, and minus u to the power of 2. And now I can close my square root sign. Okay, let me check. Yeah, we got to the right place in the right form, and that's what usually people use. Although sometimes it's maybe more convenient to start with this integral, right? Because maybe it's easier to see r's on the picture, right? And you can start from this, and only then, once you set the whole integral up properly, only then you can move to this integral. Actually, that's what we're going to do, like maybe in 10 minutes, right? We're not going to use integral in this form. We're going to use in terms of r, because again, when you draw the picture, r is in front of you. You don't have to invert them. Right. So can be convenient in setting up the problem. Right. And of course, in your homework, you will have to apply this integral. Again, as I said before in the previous class, at this point in the previous years, I would go and use this integral to solve Kepler's problem to get elliptical orbit. And this semester I decided, you know what, I will allow you to do that, right? So I just scanned my notes, right? Posted in Blackboard, probably you saw them, right? So you can read by yourself, and you'll have to sort of reproduce those steps, similar steps, but for spring force. Right. So instead of force of gravity acting between particles, so you have a spring force, and you're supposed to get again elliptical orbit, but ellipse will be positioned slightly differently. Right. It will be shifted, right? Not like in the Kepler problem. In the Kepler problem, when you get the equation of an ellipse, it's not canonical. Right? It's slightly off the canonical form, but when you solve the problem with the spring force, you will end up with a nice, pure canonical form of the equation of an ellipse. Right. Okay, so that's what you will need, and yeah, you should be able to do it by yourself, because it's just a question of doing it diligently. Right. Okay, so I will skip these 3 pages first time, because again, the goal is to why we started covering all this, so that we can discuss scattering. That's the major goal of this chapter, right? For us. So now let me write scattering, or maybe like in the book, Introduction to Scattering. Yeah, let me just write scattering. And, so so first of all, some introduction to scattering. We have to discuss it. Why scattering, although it's under the roof of central force problems, right? But it's so much more complicated. Some crazy formulas, right? Really complicated formulas. What's so special about the scattering problem? Because effectively, it's the same. Look, what how okay, what do the people who work in atomic physics usually do? They try to get, for example, the structure of some atoms, right? Or maybe they want to get information about the force which those atoms or scattering centers expose, right, or create around themselves. So they want to see that information. So maybe I should write that first. So this is used to study forces atomic structure of a target, right? And then we will try to analyze what's what's wrong with the whole picture, right? So let me write this. Collision, okay, basically scattering, right? It's a tool to study forces, atomic structure of some target, of a target, right? Okay, so to start with, let's do you remember how universal law of gravity was introduced by Newton, what 300 years ago or so, maybe 250, I forgot, right? So first, Tycho Brahe, right, for long time with his telescope, he observed planets orbiting around the Earth, around the sun, not around the Earth, right? All right, and so he recorded diligently all those data, all that information. Then Kepler came, and he diligently stared at that data for a long time, and he found some relationships, some patterns, right? So that planets are moving in elliptical orbits, that aerial velocity is constant, then that square of the period is proportional to the cube of the semi-major axis. So he found all that. Then Newton came. Right, Newton came, and with his sort of theoretical approach, he managed, based on those results, those data, he managed to write universal law of gravity. That F equals G m1 m2 divided by r squared. That's the result of this work of 3 people, right? Of course, more than 3, but anyway, so squeezed to 3, right? So effectively, what they did, they managed to get force that a scattering center that the Earth, the Sun, creates around itself. So they managed to get the force based on what? Based on trajectories. So they observed trajectories of planets, particles, in order to get force that the Sun creates around, right? So basically, we can say they used planets as sort of like a probe particles in order to probe a force created by the Sun, right? So they managed to get trajectories in order to get the force. And now, when we derived this equation, for example, right, we've done it in our undergraduate level course. Once you know trajectory, r, how r depends on theta, for example, of course, you need to write in a slightly different form, but basically that equation can be used also. So once you know trajectory, shove that trajectory into this formula, and you can get the force. That's what effectively those people did over 200 years or so, right? Experimentally, going through pain. But now if you know trajectory, plug it in and it's done, right? So then when these people in atomic physics try to probe those targets, effectively it's the same. But instead of using planets, they used what? They used some charged particles, right? Some electrons, protons, or something else, right? They shoot them at the target, right? Observe trajectory. And if you plug it into this equation, those trajectories, you can get forces. What's the big deal? It's exactly the same problem for those people in the atomic physics, right? So where is the trouble? Why all this theory of scattering was introduced, right? Some crazy equations, we will get to all those equations, right? So where is the trouble? And the trouble is that in the scattering, in this atomic physics, right? So all this scattering, all these trajectories, it all happens on a subatomic level, which is impossible to see. I said so bravely, right? So we can see a trajectory of the particle. No. Theoretically, yeah, we can draw it, but of course, experimentally, you will never be able to observe those trajectories, right? Of course, you can say, come on, what about the cloud chamber? Yeah, cloud chamber, but what about the resolution in the cloud chamber? Those bubbles, they're gigantic, right? More than gigantic, right? And they are on the level of what? The size of those bubbles in a cloud chamber, probably sub-millimeter level, right? Maybe like 0.1, 0.2, 0.3 millimeters, right? But for the subatomic levels, for these processes, those are gigantic, right? So the problem is, since it all happens on such a small scale, we just cannot get trajectories, right? Otherwise, the problem will be exactly the same, and there wouldn't be any reason to develop any scattering theory. Just shoot the particle, see the trajectory, shoved into that equation, and you will get the force. But the problem is, it's impossible. So it's more complicated, right? Okay, so it's a first reason. I will probably write a few things about what I'm just telling, right? But first I want to talk. Second, of course, you can start screaming. You just said, come on, it's a subatomic level, right? It's a teeny tiny distances, right? Small objects. How come that me, right? So I am with my ugly, gigantic, classical mechanical tools getting into this sophisticated world, basically of quantum mechanics. how dare I am, right, to do that. True, right? But the thing is, ideas, of course, you can address, there are some problems, scattering problems on macroscopic level. There are some, of course, microscopic. Of course, the ideas are very similar, right? So, of course, some ideas which we are going to introduce now can be used and is used in the world of quantum mechanics, right? Also, when we derive finally, probably next class, the Rutherford's formula, the formula will be exactly the same, luckily. So it doesn't matter if you use sophisticated tools of quantum mechanics to derive that, or ugly, gigantic tools of classical mechanics. You will get exactly the same results. It happens, right? So, right. Okay. So that's the problem. And of course, so since you cannot observe a trajectory of one particle, so what can be done in this case in order to somehow get information about that scattering center? Send a massive number of particles instead of one particle and observe their distribution, right? And then somehow extract information about the scattering center, about the target from that. So that's why basically it's sort of like a subject in the central force problem, scattering, right? Because of these problems. Okay, so now let me write a few sentences, a few words about this so that you'll have in your notes, right? Okay, so the target, I mean the goal of that I wrote, and now let me write. So, so okay, I will just write his name. So Tycho Brahe, and then what? Data, collected data, right? And then what? Kepler. It looks like my marker soon I need to will have to be replaced. So what? Analyze data. So he analyze data, and then Newton got the force. Newton got. Why so suddenly started getting worse and worse? Got the force. It was reasonably nice over here, and suddenly, okay. Let me get the second different marker. So he got the force. So basically, what they managed to achieve, they managed from orbit. Okay, this will be a little bit of time. From orbit, they managed to get the force. Okay, it looks a little bit worse. It's just because when you open the new marker, I don't know, for whatever reasons, this new expo, it takes like a few minutes to, to sort of like warm them up. Right. And only then they start writing nicely. So they managed to get the force, right? And so we can do it, and no, it's uglier. We can do it now using this equation, right? So that equation, which, okay, I can write it in a, okay, let me write in the same form, minus L squared over mr to the power 3 equals fr, right? So we can do it now using that equation. So as I said, then similar idea can be used. Similar idea. No, it's also getting worse and worse and worse, right? So I have to, right? Similar idea can be used in atomic physics. In atomic physics, right? To find forces of atoms, etc. Right? To find forces created by atoms. Right. And as I said, if you have, for example, this is scattering center, right? And if you just observe a trajectory, right, you should be able to get the force, right? So trajectory, right? So you can get from orbit, you can get a force. But again, as I said, the trouble is that you cannot observe that trajectory, right? But we can not observe or get uh, uh, those trajectories. Cannot get a trajectory. Trajectory. We cannot observe a trajectory, right? The system is too small. A system is too small. Too small, and probably I will write subatomic level. Right. So that's why we need to use many particles, right, in order to analyze. So solution, use many particles. And develop a new kind of theory, right, which will allow to get information about the target, analyzing distribution of many scattered particles instead of one. Right? Otherwise, it will be exactly the same like what Newton and Co did, right, 200 years ago or so. There wouldn't be anything new. Right. So I think I mentioned everything about this part. And now let's start developing this theory. Of course, underneath all of that theory will be all this, right? And you will see when we're going to use these ideas. Right? So first, we need to introduce important parameters, which we need to describe the system. Right? Okay. So now I will probably separate this. I will probably put a new big bullet, right? And two important parameters, right? So let's introduce two important parameters. I think I have enough space to draw a picture here. Yeah. So let's assume that this is our target. Okay, let me estimate the amount of space. Yeah, this should be enough here. So let's say this is a target. You know what, now I'm writing target, and every time when I pronounce it, and I hate that stores target, because these brands, they just ruined names, right? So now whenever people say Amazon, it's a first association, the company, and it's not the fourth. Damn it, I hate it. When people say Tesla, usually people think about the car, not about the great guy. Now Target also, whenever I write Target, immediately this red, something red appeared in my eyes. These brand names ruining the language, right? Right. So Target, anyway. All right. Especially I hate Tesla about that, right? Because I remember like a couple of years ago, I teach physics too, and of course at some point I have to talk about Tesla. Right? I decided to Google just word Tesla, entered, pressed, and it took me 10 Google search pages to go through before I found the first website about Nikola Tesla. After that, I started hating Tesla with all my, car with all my heart, right? It's ridiculous, right? Probably after another generation, people will forget that name Tesla means just the last name of the great engineer. Nothing personal about the car, just that's my reason. Right. So let me draw the line, right? Just go through the target. And let's assume that we shoot a particle. For example, this is our particle at infinity, and this is the velocity at infinity, right? So basically, at infinity, it moves along this asymptote. So basically, that's the asymptote. Okay, almost horizontal, right? So first parameter which we are going to introduce is the impact factor. It's basically the shortest distance. Maybe I should write, so this is initial velocity v naught, right? So it's the shortest distance between line of motion or asymptote at infinity or direction of velocity at infinity and the scattering center target. So basically this distance. Some books use letter B. This book uses S. Right? So I will use red because that's one of the most important parameters, and that's S. And probably I will write, yeah, I can squeeze it on top, right? So first, S is the impact parameter. Impact parameter. Okay, describing what it is, it's kind of lengthy. You got the idea, right? Then, next, of course, this particle will be scattered. So it will start moving closer and closer and closer, feeling the force will get stronger and stronger. And of course, at some point, it will change its direction. And let's assume that after being scattered, the particle will fly along this direction. That's asymptote at that infinity, right? But of course, you have to realize that particle will not fly this way. No, 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 no. Relative to this line over here, I will draw in a second. There must be symmetry, what you see here and what you see there. So you see between this line and this trajectory, there is a S. Over here, there must be similar distance S. So the particle will actually be scattered along this direction. So let me draw that auxiliary line. No, actually, this is auxiliary line. This is the true asymptote, right? So it will travel actually along that direction. So which, let me use blue. So this will be the trajectory of a particle. So symmetry is relative to this closest point, which is called periapsis. So relative to this line, there must be symmetry, what you see here and what you see there, because we have central forces, right, spherically symmetric. So if we have here S impact parameter, of course, there must be S over there. So this asymptote shouldn't go through the target. No, no, no. It's slightly offset by S, right? Maybe I can emphasize that this is also S, right? Okay, so now, as a result, now we need to introduce parameter which will describe where the particle goes at that infinity. And to do that, we use the scattering angle, all right? Scattering angle, it's an angle between this asymptote and that asymptote. Or we can say it's the angle between velocity at this infinity and velocity at that infinity, right? So as a result, we can say it's either this or that. In my notes, I use this angle, right? But of course, you see it's the same, right? So this. Or it's also, I can draw it over here, right? It's the same angle, right? So theta capital, scattering angle. At some point closer to the end of the class, we will introduce angle theta small. Careful. This is theta capital, right? Capital. To avoid confusion in the future, right? So, I will write underneath. And the second parameter is, okay, I just said about capital and small and wrote what is wrong. Theta, scattering angle. The scattering angle. Right. Okay, I can also write, so it's the angle between v sort of initial and direction of the final velocity, right? So if here, okay, I actually use v naught, okay, I can change from 0 to sub I, not a big deal, right? And there will be v final, right? So v final, right? Or angle between asymptotes, right? Then let me check if I mention everything which I was planning. Yeah, so this is probably I should also write down. So it's r equals to infinity, and of course here it's r equals to infinity, right? Ah, yeah, here's what I wanted to mention. A range of theta. So when there is no scattering center target, or maybe so weak, so then theta would be what? Theta will be 0, right? No scattering angle, I mean no scattering center, the theta is 0, right? So I can write that theta minimum is 0. But what about theta maximum? If we had a head-on collision, so if this particle goes straight into the target, so of course it will bounce back. It will be bounced back, right? So in that case, the angle will be pi, right? So theta maximum will be pi for head-on collision. Theta maximum is pi, and probably I will write for head-on collision. For a head-on collision, right? That's pi, right? Okay, so that's, and now, of course, at some point, sooner or later, we will start writing some formulas, right? And of course, which will describe the scattering, right? And of course, those formulas will depend on S and theta, right? But are they dependent, S and theta? They should be dependent. They are dependent, not should be, they are dependent, because you can easily imagine, right? So if S, for example, at this level, so let's say we have some scattering angle, but if you start increasing S, scattering angle will become smaller and smaller and smaller, right? Or if you start reducing S, right, of course, scattering angle will become larger and larger and larger. So they are dependent, right? How the dependence, of course, it will take us some time to get the dependence, right? It's one of the goals of today's class, but they are dependent. And as a result, of course, our final result, our final formulas, which we will derive, should depend only on one parameter. Which should that be? Should it be S or should it be theta? Which parameter should we take as an independent parameter? And then the other one will be dependent from the practical point of view only. Because we pretty much, what we've been doing, we're pretty much trying to derive formulas which experimental physicists can grab and use in their experiments, right? So we're just basically giving them some, simplifying their life, right? Okay, I think it's more or less obvious. Look, S, again, it's a subatomic level, right? It's a world of quantum mechanics, basically, right? Which no one can see, right? Unless it's a classical mechanical approach, right? But of course, most of this stuff is used in atomic physics, right? Of course, S is too small in order to measure it experimentally. So of course, S cannot be measured experimentally. Of course, writing down theory, yes, we can draw a nice picture and introduce it, but experimentally, yeah, good luck with that, right? So of course, but theta, what a big deal, right? So this particle will fly for, I don't know, a few meters to the target, and of course we can easily, and we know where the target is approximately, right? So we can easily measure with a reasonable accuracy, we can measure angle theta. So obviously in this case, from the practical point of view, theta must be used as an independent parameter, right? Okay, and of course at some point, not at some point, probably, I hope today we will be able to connect these two parameters, right? Okay, let me write that down because it's important that theta will be our, we will need this integral, but we can easily restore it later because we have nodes, right? Okay, it's almost a year of teaching from a room, from the apartment, so I'm getting tons of markers here. I need to start dumping them, right? Okay, so since S is too small, theta will be treated, or used as an independent parameter, as an independent parameter, right? And of course, S will be a function of theta, right? And theta, of course, can be measured experimentally. Okay, so now let's start setting up the problem. Okay, I will put a new bullet. So we introduce these two important parameters, and now, so of course, we will have to use tons of particles, identical particles. By identical, I mean what? The same mass and the same energy. Basically, you send them through some accelerator, and as a result, they're supposed to get out with more or less exactly the same total mechanical energy. So that's what I mean by the same total mass, the same mechanical energy. Okay, in this case, since it's of course, we shoot the particles from infinity, of course, it's a kinetic energy, basically kinetic energy, because at that moment, of course, the target is not, they don't feel the target, right? So let's write, consider a wide beam of particles, right? Beam of identical particles, wide beam, of course, wide, it means infinite. Beam of identical particles, right? Probably I will write mass m, total mechanical energy E, and now I need to, okay, I will draw the picture, start drawing picture a little bit lower. Now let me write a couple of additional pieces of information, very important, which we will use, right? Yeah, of course, moving towards the scattering center, so of course target is given, right? And we're going to use two assumptions. Assume, first, no absorption. Of course, particles absorption of particles, right? Actually, now I realized what else I missed. I forgot to say, right? But anyway, so no particle absorption. What does it mean? It means that you have to provide this mechanical energy should be large enough so that particles experience unbounded orbit. Because if a particle experience bound orbit, it means what? They will be trapped by the target, right? So for example, like it comes to the target, right? And starts circling. It's for us, it's lost. We want to get particles out so that we can extract information from their motion, right? But if it starts circling over here, it's lost in action, right? Or elliptical orbit, of course, we're going to assume that all particles which was sent from this infinity will be scattered and collected or detected by us at that infinity. So no particle absorption. And what I forgot to mention when I was giving this introduction, that of course now we will have to deal with unbounded orbits, because if orbit is bound and we cannot see that, for us it's useless. So we need to provide a significant amount of energy so that it will fly through and we can extract some information, whatever is possible, from their motion after they scattered, right? So of course now it's an unbound orbit. So no particle absorption, that's the first assumption. So no, we're going to use it, this fact, to derive what needs to be derived. No particle absorption. So basically conservation of particles. But of course, do not assume that there is a such thing like conservation of particles. There's nothing like that, right? If you create a box, if you shove tons of particles right into that, some neutrons, electrons, protons, and open it up after a year, number of particles will be completely different. Of course, the total charge will be conserved, right? But number of particles, like neutron, can be within 100 seconds can create electron, proton, and I think antineutrino, something like this, right? So, but in this case, we're going to use the time so that nothing will happen to those particles, right? So we're going to make this assumption. Then, and the second assumption, we're going to assume that this scattering is elastic, so that the total mechanical energy of the particle as it flies stays the same. Right? Because otherwise, in that integral which I just erased, you remember we had E. E will be a function of something, of some position, right? It will make life ridiculously complicated. And of course, this assumption that energy stays the same, it's reasonable, right? Everything happens in a vacuum, right? So there is only one scattering center. So it's quite a reasonable assumption. Right? So second, we're going to assume that we have what? Elastic scattering. Elastic scattering. So basically energy stays the same, which way I wrote. So E is constant. E is constant. You know what, since I mentioned about the constant, I was planning to discuss that a little bit later, but let me raise that now. What else is constant for this motion? We derived it already, right? You remember angular momentum of the particle, that L small, right? So what's the major difference between E and L? Of course, you can say, come on, you're comparing apples and oranges, right? This is the angular momentum, this is mechanical energy. What are you saying, right? So no, in terms of, I even don't know how to say, right? There's a very important difference between how L is constant and how E is constant. And probably without torturing you, let me tell you immediately. So what's the difference? E, total mechanical energy, is constant pretty much as particle flies, E stays constant. But at the same time, there will be a gazillion number of other particles flying. And for all those particles, E is also exactly the same. Pretty much over the whole this picture, it doesn't matter where you look, energy will be exactly the same, right? But L, angular momentum is only constant for a particular particle. If you take, for example, this particle and follow that, L will be constant at any moment. But if you jump to a different particle, of course, L will be different, right? Because the impact parameter will be different. And of course, we're going to write that L in terms of S. So L and E are, yeah, constant, but E is truly constant everywhere because we provided the same total mechanical energy for all particles, right? Okay, so they're constant, but there are details, right? Okay, and so now it's time for me to start drawing a big, and I'm trying to draw it nicely because it's a very important picture, right? So let's assume that I need to estimate the amount of space that I might need. Yeah, probably I will position my target over here. Make sure that you have above enough space and below enough space. Right, so let's say this is our target. Right, so let me, right, so it's our scattering center target. Let me draw this auxiliary line, line of symmetry, basically, right? because we have basically cylindrical symmetry. All right. Then, of course, we're going to shoot tons of identical particles. Right. So with the same mass and the total and the same, okay, kinetic energy initial, but of course that's the total mechanical energy. Then, all right, next, let's look at particles which goes through this thin cross-sectional area. And of course, I'm going to draw it sort of centered on this line of symmetry. So let me pick, you know what, let me use blue. Yeah, let me use this. So let's say this is our thin cross-sectional area of radius S, impact parameter, and its thickness is ds. Thin cross-sectional area, right? Okay, and now let's try to follow the particles which go through this ring. Okay, maybe I should highlight it something like this. Okay, and so now let's try to follow these particles. Let me start with this one, which goes through this point. So the impact parameter S, right? So of course it will travel along these. This is the asymptote, right? And of course, after scattering, now I need to draw this asymptote, right? So it will go probably, let's assume along this direction, right? So it will be this and right. So that will be the asymptote for these particles. And I will probably use this black, right? So okay, let me draw arrow. Right. Okay, then let's draw the same for the trajectory of a particle with the impact parameter of S plus ds. Right, so it will go, you know what, maybe I will use black still. Of course, this particle will be, of course, scattered at a smaller angle, right, smaller than this. So it will most likely go probably along this trajectory. I mean, along this asymptote. And I guess it's, again, it's offset by S, by the impact parameter. So this particle will go like this. Right. Now, so particles, all the particles which goes between these two S and S plus ds will be scattered into that direction. So now, of course, from experimental point of view, because we remember we're trying to prepare a tool for an experimentalist. Of course, they're going to position somehow their detectors to detect these scattered particles. Of course, it's up to them how to position those detectors, but it would be quite, okay, I want to say stupid, but silly if you would position them, for example, on a flat surface, right? Because we have most likely some spherical, cylindrical symmetry, right? It's better to use that. And of course, it's better to position your detectors on a spherical surface centered on the target, right? Because we have forces, we have spherical symmetry. Of course, it makes sense to expect spherical symmetry and use that symmetry, right? Okay, so now let me position these the detectors. All right, so let me draw this surface. Right. So there we're going to have detectors. Detectors. And of course, centered on the target. Okay, now it's time to say a few words. Where is, not a few words, now we need to show where is the scattering angle. So we see S, but scattering angle. Of course, strictly speaking, the scattering angle, let me use green. So scattering angle is this, right? So this is, strictly speaking, scattering angle. And this is d theta, right? Like here, this, right? But, so pretty much these lines don't go through the target. But compare distance to the target, probably several meters. Distance between this point and that target, as well as this S, teeny tiny, right? So it's if you measure theta from the target, it's not going to affect anything. Pretty much your experimental error will cover that with, right? So basically, as a result, yeah, strictly speaking, this is theta scattering angle, but we're going to measure theta from here to this point, right? So that's what we're going to use here as a scattering angle. Small cheating, but again, as I said, relative to these meters, these distances, it's much less than teeny tiny, right? Again, subatomic levels, right? A few nanometers, if not less, right? And relative to several meters. It's, right. Position your detectors, or some uncertainty in your detectors will give more error, right? Okay, so as a result, I need to, let me erase with this so that it will, with less lines, I will have less lines. And now, so let me connect this with that. So this will be our angle theta between this line and that line, right? Right, so I can show that now this is my angle theta, scattering angle. Right. So maybe I will write, so this is actual, but that's what we use. So this is actual, and this is used one, and this is used, the angle which we use. And of course, we will have to introduce also d theta, and of course, d theta will be angle between, of course, this point and, I mean, this line and that line, right? So you see, these are two trajectories crossing the surface where detectors are, right? And these are two lines which connects those 2 points with the target. So as a result, this is d theta, right? D theta. Whew. Right. So now, as a result, now we introduce theta. We can say that all particles which goes through this ring will be scattered into the ring of this width, right? Because again, there is a symmetry relative to this line. So now, as a result, I can draw something like this. So it means that all particles which goes through this thin cross-sectional ring over here will be scattered into this ring with thickness. What is thickness? So this, okay, let me use, of course, this is R. It's the radius, of course, from the target to the places, to the sphere where detectors are. Of course, as a result, this thickness of this ring will be R times d theta. So this thickness is R d theta. And of course, we can also write down the radius of this ring. I'm trying to say sort of infinitesimally thin, but something is stopping me. Right? Most likely, yeah, it will be still infinitesimally thin, right? So, and this radius is, of course, this is still radius, I mean r, and this is theta. So r sine theta, trivial thing, right? So it will be r times sine theta. You know what scares me? Most likely I will be able to finish this, but of course I will need this picture for the next class, so I will have to redraw it, of course, before the class. Okay, so now let me check if to make sure that I mention which I was planning about just general. Yeah, it looks like, yeah. Now, I'm going to introduce a few, like for example, area of this ring, area of that ring, and some other parameters. Basically, I'm pretty much now I need to prepare a few ingredients in order, and of course I will use them probably most likely next class, right, in order to write differential cross-section and so on. But for now, we need to write a few kind of first looking like a random things. For example, let's write down the area of this ring, but we will need it when when we will need it. So I can write this, of course, area will be, I think I wrote it as dA, yeah, dA. dA, of course it will be 2 pi s ds, circumference 2 pi s, and of course thickness ds. Now area of this. Okay, I don't want to highlight because then I will cover my d theta and this theta, right? So that's why I should have highlighted this ring, but don't want. So now this area, of course, will be written as dA prime equals, so it will be 2 pi r sine theta, 2 pi r sine theta capital, right? And then times the thickness, r d theta. R, okay, I'm getting into this, r d theta. So that's the area of that ring through which particles will be scattered. Okay, those particles which went through the ring. And of course, at some point, we will also need the solid angle, all right, which sort of supports this ring. Okay, that's simple. Just the area divided by r squared. Actually, let me write first 2 pi r squared sine theta d theta. And now let me write the solid angle subtended by this dA. So solid angle d omega, of course, in stereoradians, it will be dA prime over r squared by definition. So it will be 2 pi sine theta d theta. Okay, so of course we will need this. And now let's start introducing intensities. And I need to erase this. So intensity of incident beam and intensity of scattered beam. And those intensities are introduced in a different way. Okay, that's why I don't like using new markers, because for half an hour it creates this mess which is impossible to erase. I will have to wash it. Okay, intensity. You remember in optics, how do we define intensity of a beam of light, right? It's basically amount of energy per unit area and per unit time. Basically, you restrict energy in space per unit area and in this direction in time, right? So very similar definition of intensity will be used or is used to define intensity of the incident beam, but intensity of scattered beam will be defined in a slightly different way. Okay, so now let's introduce intensity, as I said. Which way call it? Okay, intensity over incident beam. Okay, so let me write intensity, or maybe I just should have written incident intensity. Intensity of an incident beam. Actually, probably I should write the incident beam. Okay, so we're going to use letter I. And as in optics. But now, of course, instead of amount of energy, we're going to talk about the total number of particles per unit area, per unit time. Right. And I will write it like this. So number of particles, it's an incident. I will write prime. I will use prime, and you will understand in a second why I used here prime. Because I'm not going to use this number of particles. I will use slightly different number of particles. Right. So number of particles per unit area, so I need to divide it by dA, and per unit time I need to divide it by dt. Right. Okay, and I will write, so it's a number of particles per unit area per unit time. Right. Okay, so now, as I said, I don't want to use this number of particles later on in my derivation. I want to use a number of particles per unit area in dA. Pretty much all the particles which goes through this ring. That's what I want to use. So I will introduce this as dn. Okay, let me open my explanation box. So dn prime incident over dt. Let me call it as dn incident. Okay, and that is number of particles per unit time, right? You see, I'm still dividing it by dt and in dA, because dA I left outside, so it means that number of particles which went through this cross-sectional area dA. Okay, so now as a result, of course, I can write, so it equals to dn incident divided by dA. And what I want to write this number of particles. It will be I dA. So I will need that again, most likely in the next class. Let me frame it, because at some point I will start searching for that. Something similar, but now for scattered beam. And of course, I will introduce intensity in a slightly different way. Now it will be number of particles, still per unit time, but now it will be per solid angle. Instead of area per unit area, we're going to use per solid angle. Okay, let me write that down and we'll call it a day, right? So let me write similar for the scattered beam. So now scattered intensity. So it's a first small bullet, now scattered intensity. Scattered intensity. I'm surprised that marker is still not getting better, any better. What happened? I started using a new solution to clear the board. Maybe this solution is spoiled the surface. So scattered intensity. Of course, we will use I prime. Oh, it's something really fishy, right? So it will be number of particles, scattered particles. Again, prime. I use prime. And divided, but now d omega and dt. So it's a number of particles per unit time in d omega, right? Yeah. And again, in the same way, let me introduce number of particles per unit time in d omega. Pretty much particles which go only through that. Right, so it will be, let me again introduce that this dn prime scattered divided by dt, it will be my dn scattered. Right. So as a result, of course, I can write similar. Okay, let me write immediately. So it will be a number of particles scattered per unit time in d omega. It will be equal to the scattered intensity times d omega. Right. Okay, so let me frame this. Wow, it's probably the ugliest board I've ever had, right? Here, so black, right? Okay, so now pretty much we're ready to introduce differential cross-section, right? Differential cross-section, by definition, just relates these two intensities. That's it. And then we will, from this definition, we will get the definition which books offer, or this book offers, right? I'm not a big fan of that definition, maybe because I don't work in atomic physics, but when I first read that definition, kind of, why so complicated? Why is this, right? But once I worked it out through the intensities, it's much better, at least for me. Right? So differential cross-section, let's introduce sigma. Differential cross-section is introduced in a very simple way, just relating these two intensities, right? So I can write, so I prime equals to sigma times I. So that's how we can introduce differential cross-section, right? Basically, and of course you can see that units of sigma must be units of area, because what's the difference between this intensity and this intensity? Here we have meter squared, here we have nothing, stereodirans, right? Of course, this must have units of area, right? And so from this point, next class, additional line, a couple of lines, we will get definition of differential cross-section, which book offers. Then we will move actually to find the relation between S and theta, because that's very okay. Not first we will get expression for sigma. Yeah, first we'll get expression for sigma in terms of S and theta, and then of course naturally we will have to find the relation between S and theta.